Hello Math 200 students. We're on section 6.2. This is 6.1 is about confidence intervals for when you know the population standard deviation sigma. 6.2 is about the same thing, except for this is confidence intervals when you don't know the population standard deviation sigma. And so if we use the z interval, the z distribution or z interval for 6.1, we are using the t interval, t distribution in 6.2. In many real-life situations, the population standard deviation is unknown. So how can you construct a confidence interval for a population mean when sigma is not known? For a random variable that is normally distributed, or approximately normally distributed, you can use a t distribution. If the t distribution of a random variable x is approximately normal, then t equals the difference between the sample mean and the population mean divided by the sample standard deviation over the square root of the sample size. All right, and that follows what's known as a t distribution. Critical values of t are denoted by this symbol t sub c. Here are several properties of the t distribution. The mean, median, and mode of the t distribution are equal to 0. The t distribution is bell-shaped and symmetric about the mean. The total area under the t distribution curve is equal to 1. So far, it sounds a whole lot like the z distribution, doesn't it? It sounds a whole lot like the standard normal distribution. But it's going to start being different here. The tails in the t distribution are quote-unquote thicker than those in the standard normal distribution. The standard deviation of the t distribution varies with the sample size, but it is greater than 1. The t distribution is a family, so that's what's different. Part 5 is what's different. The standard deviation of the z distribution for the standard normal distribution, it was 1, but this for the t distribution it's a little bit more than 1. So it's a little bit more spread out than the standard normal distribution. The t distribution is a family of curves, each determined by a parameter called the degrees of freedom. The degrees of freedom, sometimes abbreviated as df, are the number of free choices left after a sample statistic such as x bar is calculated. The number of free choices left. We'll talk more about that in a minute. When you use a t distribution to estimate a population mean, the degrees of freedom are equal to 1 less than the sample size. As the degrees of freedom increase, the t distribution approaches the standard normal distribution, as shown in the figure. After 30 degrees of freedom, the t distribution is close to the standard normal distribution. So in other words, once your sample size is getting up closer to 30, you're starting to get pretty darn close to the standard normal distribution. So why are the degrees of freedom equal to the sample size minus 1? Here's kind of an analogy I can make with you. And actually it explains it right here. The number of chairs in a classroom equals the number of students. 25 chairs and 25 students. Each of the first 24 students to enter the classroom has a choice as to which chair he or she will sit in, right? If there's 25 chairs, and then the first 24 students will have some choice about where they sit, although the choices are getting narrower and narrower. But the 25th person, and let me read it as the book says it, there is no freedom of choice, however, for the 25th student who enters the room. They only have one desk to sit in, so it's not a matter of freedom at all for them. So that's why the degrees of freedom is always equal to the sample size minus 1. So if there's 25 students, the degrees of freedom would be 24. All right, let's go on to the next page. Finding critical values of t. Find the critical value t sub c for a 95% confidence interval when the sample size is 15. Okay, they are showing you how to do this in this solution by using a table in the back of the book. But I'm going to show you, and that's fine. If you use the table, no problem. But I'm going to show you how to do it in your calculator. All right, again, what you're trying to find, I probably need to draw it for you. What you're trying to find visually is you're trying to find what are these values right here such that 95% of the data are inside of those values. So what's this value and this value? So you could do, what you'll do is you'll go to your calculator, you'll go second distributions. And when we did this before in 6.1, we used the inverse normal to find the z sub c value. Well, for this unit, we're using t. So it's, instead of the inverse normal, it's the inverse t. So you use option 4. The area, all right, the area is something you're going to have to think, use some more thought on. Like on the previous unit, we were able to choose left, center, or right. And because we could choose center, that made it a lot easier. We just put 0.95 in there when it wanted to know 95%. Or we could have done, remember I showed you how to do a left tail for that as well. The only way this is going to work is if you use a left tail approach. So here's what I mean by that. Okay, it's only going to give you, it's set up to do a cumulative distribution. It's set up to give you the cumulative area and the value for that cumulative area. In other words, everything to the left of that area. So it's set up to do a left tail. So here's how you got to think about it. If it's 95%, so if we want a t sub c value for 95%, that means 95% is in the middle of these two values. So how much is in this tail? Well, you got to think about it as there's 5% left over to go into both of these tails. So it's got to be split in half. So that means there's only 2.5% here. And I guess you could say there's also 2.5% here. But we only care about the left. So we're going to put for the area 0.025. Now this would, I don't want to confuse you, but this would also work if you used everything, because you would get the same value here as you get here. It's just one will be negative, one will be positive. So this would also work if you, let me draw it right here. If you do, if you do it right here and think how much area is to the left of that value, it's all of that. So it's the 2.5% plus the 95%. So that would be 97.5% right there with only 2.5% left over. So we could put an area of 9.975 as well. That would also work. But whichever one of those ways makes more sense to you is fine. But let me go back to my calculator. I'm going to put 0.025. And let me try, I can't remember what the sample size was. Their sample size was 15. So how many degrees of freedom is it then? It's always one less than the sample size, so the degrees of freedom is 14. And we click paste, and it should give us the answer. Negative 2.1448, or negative 2.145, depending on where you want to round it. And that's exactly what we have here. The t sub c value is 2.145. Again, don't worry about it being negative or positive, because on one side it's going to be negative, on the other side it's going to be positive. So you're just given the absolute value of that as the t sub c value. Interpretation. So for a t distribution curve with 14 degrees of freedom, 95% of the area under the curve lies between positive or negative 2.145. When the degrees of freedom you need is not in the table, use the closest degrees of freedom in the table that is less than the value you need. For instance, if the degrees of freedom equals 57, the closest one you'll get to is 50. Use 50 degrees of freedom. This conservative approach will yield a larger confidence interval with a slightly higher level of confidence C. Again, that's only if you're using the table. If you're using your calculator, you don't have to worry about that. You can just put in, if it was, you can just put in 57 as it is. You don't have to worry about that part. So also just to note this, that as the degrees of freedom increase, the t value and the z value are going to be closer and closer to each other. So just interesting piece of information there. So confidence intervals and t-distributions. Constructing a confidence interval for mu when sigma is not known using the t-distribution is similar to constructing a confidence interval for mu when sigma is known using the standard normal distribution. Both use a point estimate x bar and a margin of error e. When sigma is not known, the margin of error e is calculated using the sample standard deviation s and the critical value t sub c. So the formula for e is, and this is very similar to what we looked at before. The margin of error in 6.1 was z sub c and then sigma over the square root of n. Well, now we got t sub c and s over the square root of n. So it's a very similar process. Before using this formula, verify that the sample is random and either the population is normally distributed or n is greater than or equal to 30. If you want to pause this and read these guidelines and see if they make good sense to you, feel free to do that. All right, example 2. You randomly select 16 coffee shops and measure the temperature of the coffee sold at each. The sample mean temperature is 162 degrees Fahrenheit with a sample standard deviation of 10 degrees Fahrenheit. Construct a 95% confidence interval for the population mean temperature of coffee sold. Assume the temperatures are approximately normally distributed. All right, we don't know, and this is what you're going to have to do on a test. You're going to have to determine, are they giving me the population standard deviation? If they are, then you will use the z interval, the methods from section 6.1. If they don't give you the population standard deviation, which is what we have here, we don't know the population standard deviation. We have the sample standard deviation. We don't have the population standard deviation. Then we're going to use the t interval to construct the confidence interval. So we go to our calculator and we go to, what is it? I think it's stat and then tests, and then go to, instead of option 7 z interval, we go option 8 t interval. And again, we could put in data if we were given a set of data, but we're not given a set of data. We're given some statistics about a set of data. X bar was 162, right? 162. 162. S sub x, that's the sample standard deviation, and that, I think it said that was 10, I believe. And the n is the sample size, which was 16 coffee shops. 16. The older versions, I think instead of asking for n, they ask for df, degrees of freedom. And if that's the case with your calculators, you wouldn't put 16, you would put one less than that. You would put 15 because that would be the degrees of freedom. But for the newer versions, they just ask for the sample size n, so you just put 16 in that case in this example. And the confidence level, doesn't it ask for 95%? Yeah, 95%. So 0.95. And calculate that thing. And it gives me the confidence interval. We can be, with 95% confidence, the population standard deviation for the temperature, a mean temperature, is between 156.67 and 167.33 degrees Fahrenheit. In fact, if you wanted to, you could use this method to find the margin of error as well, just like we did in the previous unit. If you want to find the margin of error, you could use the formula as I showed you earlier in the video, or you could simply find the t interval and then subtract either one of these endpoints with the mean, and that will give you the margin of error. Or similarly, you could subtract these two endpoints from each other and then take what you get there and cut it in half, divide it by 2, and that would also give you the same margin of error. All right. The other way you could construct the confidence interval that's not as easy as what I just did would be to find the margin of error using the formula that I showed you earlier in the video, and then like using this, and then add that margin of error and subtract that margin of error with the mean. So that does the same thing. So interpretation: with 95% confidence, you can say that the population mean temperature of coffee is between those two temperatures. Moving on. Again, constructing a confidence interval. You randomly select 36 cars of the same model that were sold at a car dealership and determine the number of days each car sat on the dealership's lot before it was sold. The sample mean is 9.75 days with a sample standard deviation of 2.39 days. Construct a 99% confidence interval for the population mean number of days the car model sits on the dealership's lot. Okay. What are we given for the standard deviation? We're given the sample standard deviation, which means we're going to use the t, not the z interval. So go, what is it? You just go stat, click over to tests. Option 8 is the t interval. We're entering stats instead of data. X bar, wasn't it 9.75? 9.75. The sample standard deviation was 2.39. The sample size is 36. And the confidence level was 0.99. Calculate, and here's our confidence interval. We can say with 99% confidence that the mean number of days that model sits on the lot is between 8.665 days and 10.835 days. Okay. I think this is an interesting historical reference. William Gossett, who lived in that time period, developed the tea distribution while employed by the Guinness Brewing Company in Dublin, Ireland. And I think that's funny because I don't know if you've ever seen the Guinness commercials, but I don't remember how many years ago, 4 or 5 years ago, Guinness had commercials on TV where the two guys were sitting in a bar and they're talking about, I don't remember what they're talking about, but they come up with some kind of solution to a problem, and the guy goes, "Brilliant!" And I just think that's funny because I feel like that's kind of how this guy did his thing at Guinness. And I also think it's funny that he came up with such a grand and ingenious idea, basically motivated by beer. So that's pretty funny. Gossett published his findings using the pseudonym Student. So instead of using his name, he just published his findings using the name Student. The t distribution is sometimes referred to as Student's t distribution. You can also look at page 35 for others who were important in the history of statistics. I'm sure that's a very interesting read. Moving on. The flowchart describes when to use the standard normal distribution and when to use the t distribution to construct the confidence interval for a population mean. Here we go. Question 1. Is sigma, meaning the population standard deviation, known? If yes, then if either the population is normally distributed or n is greater than or equal to 30, then use the standard normal distribution. If no, then if either the population is normally distributed or n is greater than or equal to 30, then use the t distribution. Pretty simple. Notice in the flowchart that when both n is less than 30 and the population is not normally distributed, you cannot use the standard normal distribution or the t distribution. Example 4, choosing the standard normal distribution or the t distribution. You randomly select 25 newly constructed houses. The sample mean construction cost is $181,000. The population standard deviation is 28,000. Assuming construction costs are normally distributed, should you use the standard normal distribution, the t distribution, or neither to construct a 95% confidence interval for the population mean construction cost? Well, the question is, what do they give us for the standard deviation? They give us the population standard deviation. That's sigma being known to us. So we will use the z interval, not the t interval, would be best on this problem. 25 newly constructed houses, so n is not greater than or equal to 30. But it does say to assume that the costs are normally distributed. So we're going to be able to use the z interval there. So I won't continue with that. I think this is also an interesting example here on the left. 2 footballs, one filled with air and the other filled with helium, were kicked on a windless day at Ohio State University. The footballs were alternated with each kick. After 10 practice kicks, each football was kicked 29 more times. The distances in yards are listed. So for the regular air-filled ball, you have these yards for the kicks. 19 yards, 20 yards, 20 yards, 22, 22, 22, 25, 25, 25, 25, 26, 26, and so on and so forth. And then for the helium-filled balls, you had 11, 12, 14. Now what does that mean? Oh, nothing. Nothing for that. So 11, 12, 14, 22, 23, 24, 26, 26, 26, and so on and so forth. Assume the distances are normally distributed for each football. Apply the flowchart at the right to each sample. Construct a 95% confidence interval for the population mean distance each football traveled. Do the confidence intervals overlap? What does this result tell you? I think that it would be a cool thing for you to do that example and see what you come up with. If the confidence intervals overlap, then you can't say which one truly has a higher mean distance. I think you'll be surprised by the result. I was surprised when I did it. And that is the end of section 6.2. Good luck on that assignment. I'll see you again in 6.3.